Hey everybody, last week we spent some time talking about limits, and as we get ready to begin our work in AP Calculus, we need to understand what a limit is. So a limit is a value that a function is approaching. What it means contextually is what is the instantaneous rate of change at that moment in time. So we can find a limit two ways. We can find it graphically or algebraically. On my screen here, I have a graph, and I want to evaluate this. I want to find the limit of the function as x approaches 1. So as x approaches 1 from the left, I'm getting pretty close to positive 1. As the function approaches 1 from the right, I'm getting pretty close to negative 1. Those two values are not the same. So this limit cannot be evaluated. We say DNE for does not exist. But take a look at this graph. So here it seems to be pretty continuous. There's this hole at 1, but then I have another function value up here at 1, 1. I have a hole at 1, negative 1-ish, and a dot at 1, 1. So what is the limit of the function as you approach negative 1? Wait, what? Okay, what's the limit of the function as you approach negative 1? So as I move towards negative 1 from the right, I'm kind of reaching 1. As I move toward negative 1 from the left, yep, I'm coming up here at 1 again. So at negative 1, the limit of the function is equal to 1 because I'm approaching 1 from both directions, left and to the right. Now, what if I wanted to find the limit of the function as I approach positive 1? So here's an issue. As I approach 1 from the left, I'm coming down to 1, but there's a hole. As I approach 1 from the right, I'm also approaching 1, but there's a hole. Now, my actual function value is 1, not negative 1. So therefore, I would say that the limit does not exist. So the limit, for a limit to exist, you have to be coming at a point and be equal to that point from both directions. So do you see the difference there as I approach negative 1 and as I approach positive 1? So those are two limit problems that on this graph, and then we did that limit problem earlier. So you've looked at two different graphical approaches to finding a limit. All right, now what about something algebraic? So if I wanted to find the limit as x approaches negative 2 of this function, I mean, I'm a boss at function families, but this guy is not a member of any function family I've ever met. So I can't think about this graphically. I need to think about this from a different approach, which would be algebraic. So let's try some direct substitution. If I plug in negative 2 everywhere there's an x, I end up with 0 over 8. Now 0 divided by 8 is equal to 0. That's okay. It's not a no, it's okay. So 0 divided by 8 is 0, and that's a value. That is actually the value that this graph will approach as we come at negative 2 from both the left and the right. Now in this one, we've got the limit as x approaches 0 of another function family I've never met. So I'm going to start with direct substitution, but when I plug in those zeros, I end up with 0 over 0, which is undefined. That's what we call indeterminate form. If you get something that's indeterminate, you have to try something else. Well, what do I have left to try, algebraically speaking? Factoring. Factor the numerator, factor the denominator. Does anything cancel? All right, now we're cooking because we got those x's to cancel. When I plug in direct substitution, I don't get something indeterminate. I get an actual number. Like I know exactly where 3 over 2 is on the number line. I know exactly where 0, 3 over 2 would be on the coordinate plane. So that is actually what the limit of the function approaches as you approach 0. That's what the limit of the function is as you approach 0. Now, if you don't believe me, open up Desmos or your graphing calculator, plug that into your graphing calculator, and you will see that the curve is doing something wild and crazy on the left and wild and crazy on the right. But as you approach 0 from the left and the right, you're going to be at 1.5 on the y-axis. Isn't that so cool? I just love limits so much. All right, so that's all I have to say about that. I have a circuit in the Google Classroom for you to look at. We're going to do a lot of circuits in AP Calc just because one of my favorite math teachers from Mississippi puts them on Teachers Pay Teachers, and she just loves to do circuits. And I love circuits because they're self-checking. So learn to love a circuit because next year you're going to do lots of them. And in fact, this past year, my kids have even been asking, do you have a circuit for this? If it was something that I didn't have a circuit for. All right, enough of that. So limits, go crazy. Bye, guys.